So you could separate different chemical species from each other if they have different volatilities, right? And in general, or you could visualize the differences in volatilities between chemicals by using what we call a vapor-liquid equilibrium diagram, right? So differences in volatilities can be visualized by a vapor liquid equilibrium, otherwise known as a VLE diagram. Okay? And so now I actually want to guide you through an example of a vapor liquid equilibrium diagram so that you could get an idea of how to use these sorts of phase diagrams. So I'm going to go over to these slides here. And what you're seeing here is a VLE diagram for benzene and toluene, right? And so benzene is just a simple aromatic ring, while toluene is very similar to benzene, except it just has this methyl group on top, right? It has this little extra handle, right? And so toluene, because it has this little extra handle, it has a higher molecular weight than benzene. And as such, it has a lower volatility than benzene because it weighs more. Or, in other words, benzene here has a higher volatility than toluene. Okay? And so what we're looking at is the vapor-liquid equilibrium diagram for benzene and toluene. And so on the y-axis here is temperature, and on the x-axis here is going to be the mole fraction of benzene for both the liquid and the vapor phases. Okay? And so, in other words, these are known as TXY diagrams. And so the way to interpret them is you could see that there's a sort of two black lines here, right? Below the bottom line, everything in this part of the VLE diagram is a liquid. So everything here is a single phase. Everything above the top line is a vapor. And so this is also a single phase, right, if you're at that temperature and composition. But what's interesting here is the part that's between the two lines in this little envelope. This is a region of coexistence, right? And so that's where the liquid and vapor phases are in equilibrium with one another, right? And so from this VLE diagram, you could determine, what the composition of liquid and vapor phases are that are in equilibrium to one another. And so I'm going to guide you through an example of us using this. And so let's consider the case where let's say we start out with a liquid mixture of benzene and toluene at a temperature of 65 degrees. And let's say the initial composition of benzene in our liquid mixture is 0.6. Okay? And so in this case, at this temperature, everything's a liquid, and we have this mole fraction of benzene down here. Let's now heat up the system, okay? So we're not going to add any benzene or toluene to our system. We're just going to heat it up, simply. And so what we're going to do is we're going to go draw up from here. We're going to go straight up because we're heating up the system. We're going to keep going. Everything's in a single phase. We're going to keep heating it up until we hit the black line here. Right? And so when we hit this black line, now we've added enough heat to the system so that molecules can start vaporizing. And so some of the liquid starts to become a vapor. But we have to remember that between the two chemical species in our system, the benzene is much more likely to evaporate than the toluene. Okay? And so once we hit the black line here, which corresponds to the boiling point of our liquid mixture, what we do is then we go directly to the right staying at the same temperature until we hit that top black line. Right? And so by doing that, we now have a different composition, 0.8. And so what that is telling us is it's now telling us the composition of benzene in the vapor phase. And because benzene is more volatile than toluene, right, there's going to be more benzene molecules in our vapor now. And so by using this phase diagram, we could figure out what that vapor composition is going to be. Okay? And so even though our liquid mixture had a mole fraction of only 0.6 of benzene, our vapor phase is now enriched in benzene. It's now that mole fraction in the vapor phase is higher. Okay? And so that's what happens when we boil. The same thing happens if we try going from the vapor phase to the liquid phase, right? So let's say we have a vapor that's 0.4 of benzene, and we were at a high temperature. And so if we go down, when we hit the top black line, we would then go left until we hit the bottom line. And then now, here is the composition of the new liquid mixture as the vapor condenses. Okay? The temperature in which that happens is known as the dew point temperature. So T dew. All right? And so those are the main features I wanted to point out. You know, this bottom line corresponds to the boiling point temperature of your system if you were going from the liquid to the vapor, while the black line corresponds to the dew point temperature if you're going from the vapor to the liquid. And so just to summarize things that you've seen here, that top black line, which is otherwise known as the vaporous line, gives T dew. So your dew point, if you ever hear about this from your meteorologist, that just means the temperature in which the vapor goes to the liquid. While that bottom line is what we call the liquidus line. And so that gives you the boiling point temperature. So here's where you go from the liquid to the vapor.